When dealing with uniform circular motion, we found that the x position and the y position of the rotating object can be expressed in terms of a sine function. Similarly, we found out that in simple harmonic motion, the position of the object can also be expressed in terms of a sine function. One might wonder, what's the relationship? For example, here, if I have an object rotating at a constant angular speed omega, if its angular position theta, like at this position here 2, is given this way, so we are measuring the angles counterclockwise. This is my x-axis, this is my y-axis. Now, the x position for this position 2 here is the adjacent to the angle theta. So it is x equal r cosine theta. But theta, since the object is rotating at a constant speed, is omega, the angular velocity, times time. So that's r times cosine omega t. Graphically, for position 2, this blue line, the x position, is given by this blue line here, which gives us the position in the graph here. Now, at position 3, when the angle is pi over 2 or 90 degrees, the x component is 0. That's what we see here. X component is 0. Then I'm skipping position 4. For position 5, the x component is minus 1 for this particular case. That's minus 1. The angle is pi, so that's what we see, pi. For 3 pi over 2, 270 degrees, we are at position 7. It should be, the x component should be 0. There we have it. And as we continue, we are completing a sine function. Now let's see this in action. Okay, you see it here. Now the x component in this case is in blue. So you see it here in blue. And the y component is in red. In this case, just for people who are familiar with complex analysis, the x component is called the real part. The y component is called the imaginary part. Okay. So you see here how the rotational motion is translated into a sine function for either the y component of the motion or the x component of the motion. Okay, we can also see it here. We have a blue spring and a yellow spring, and we have an object that's going to go around in a circle. When I start this, the vertical position of the mass is going to be graphed here. And as we expected, it should be a sine function. But in the same token, you notice that's the same as that blue line there. The position of the mass at the end of the spring is the same as the vertical position of the rotating mass. That's the blue line here. Of course, for that to happen, the amplitude of the oscillation of the spring has to be equal to the radius of the circle. Here we are not graphing the sine function for the yellow spring, but the yellow line here is going to follow similarly a sine function, like this one here is a sine function. The yellow sine function would be 90 degrees or pi over 2 out of phase as compared to the blue sine function.